Hello everyone, sorry for the delay and welcome back to the DDLC seminar series organized by the Ideas Labs at College University. And today's talk is about data monetization in strategic games. And it's a pleasure to introduce today's speaker, Professor Munther Dahleh. He's the Director Institute of Director of Institute for Data Systems and Systems. I'm sorry, there is some echo. Yeah. Yep. Can you hear me, Dr. Dahleh?
Yeah, I can hear you.
Yep. 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 Yeah. So Dr. Dahleh is the director of Institute for Data Systems and Society at MIT, and he's the William A. Coolidge Professor of the Electrical and Computer Science Department. And Dr. Dahleh received his PhD from Rice University in Houston in 1987, and since then he's been associated with the Electrical Engineering and Computer Science Department at MIT. And he's currently the director of the newly formed MIT Institute for Data Systems and Society, the IDSS. And previously, he held positions of associate department head and assistant director of the engineering systems divisions and acting director of the LIDS. And Dr. Dahleh is well known for his seminal contributions to the field of network systems and robust control. And the applications of such research include domains like transportation, autonomous systems, power grid, financial systems, and social networks. And Dr. Dahleh's work has appeared in economics, operation research venues, as well as eight different IEEE transactions journals, including the automatic control, the biomedical engineering, and also the network science. And Dr. Dahleh has a long list of achievements, and just to highlight a few, and he's a four-time recipient of the George Axel B. Outstanding Paper Award for the best paper in IEEE transactions and automatic control. And he's also the recipient of the Donald P. Ekman Award from the American Control Council in 1993 for the best control engineer under 35. And without further ado, I'd let Dr. Dahleh take on.
Okay, thank you for the introduction. Sorry, I'm trying to. Yes, here we are. Okay. Good afternoon, everyone. Can you hear me well?
Yep, I can hear you.
Yeah. Okay. Sounds good. Okay. So I thought today I'll make some remarks on this whole notion of data monetization in strategic games, and in particular, sort of a notion of how information gets shared in managing physical infrastructure. So I will be talking a little bit about how to put value to information. This research is in collaboration with my research scientist, Thibaut Horel, and my colleague Alessandro Bonatti and a student Amir Nouripour. Before I start, I wanted to just give a shameless plug to my new and upcoming book on data systems and society. This is the outgrowth of, well, it's sort of a reflection of the journey that we took at MIT in the founding of the Institute for Data Systems and Society. The book is not a technical book, but rather is a sort of um, uh, uh, kind of a collection of a lot of the different ways in which we can view artificial intelligence and machine learning and data science all coming together in solving societal problems, understanding the kind of the opportunity in many different ways, but also understanding the pitfalls and what can go wrong. It's a great simple read. It's not that long for a lot of the students who are embarking on this particular field, but also documents our journey in building IDSS at MIT for people who are potentially are doing something similar in a different institution. So just came out by Cambridge University Press, and I hope you find it an interesting read. I wanted to talk about the sort of the broader umbrella of a lot of the work that I've been doing in the last 7 years, which is sort of trying to understand how to come up with a marketplace for data. This is a sort of a broader question than the information design question that I'll talk about today. But data has become, of course, the most important thing that we need in order to resolve problems. I mean, now with the expansion of generative AI models and so forth, it comes down at the end of the day, do we have the right data to answer the difficult question that we're after? And is there a way in which we can actually exchange this data, communicate it among different groups in order to be able to localize the information that we're trying to solve a problem with? There was a quote that I like several years back that says personal data is the new oil of the internet and the new currency of the digital world. And I think that this is more so now than ever. Um, when you think about how data is sold or acquired, it's highly inefficient. A lot of companies, for example, will just go to Bloomberg or Nielsen or Reuters or any of these data companies and say, we're interested in customer data of some sort. They pay $10,000 for a bunch of records. And then a lot of, many situations, this data is probably not that useful to them. And this sort of tying the price of the data to the value of the data is not something that happens very often. We can imagine Bloomberg, for example, runs the stock market. So there is an operational value to the data. And so there is a tying of, that data is not really private data, it's common data. It's just that it's useful for running the market. So it's priced for the operational value. But how about other types of heterogeneous value that people extract from data? How is that looked at? You can think about 23andMe as a data market, kind of a strange data market in that you pay and you give your data. But in principle, they give you back some services that are valuable to you. And this exchange also is a fixed fee type exchange. My data could be less valuable than someone else, for example, and that tying into the value is not there. So in the case of infrastructure, this is an emerging problem that we look at in engineering, whether the physical infrastructure that we deal with are transportation system, electricity systems, e-commerce platforms, many physical infrastructures. And we always think about a digital platform that is managing sort of this particular physical structure by managing both components. One component is the actual physical space, and the second one is the interaction of people with that physical space. Okay, so and I'll give you some examples of this. And the coordination of the behavior of people is a key component in the success of how the physical infrastructure works. But of course, while you, for example, if you think of a transportation system, well, it's easy for us to kind of regulate traffic lights and how many one-way lanes that we have, and even adding toll and pricing and so forth. We can do all of this because these are physical components. It's very hard to actually manage people because you have to incentivize rather than you control. And then, and so the kind of a control theory emerging in these particular problems has these two different components. One is an actual control at the higher, in my picture here, sort of the physical part, but there's an incentive design at the lower part. And how do we do this simultaneously? Of course, is a holy grail of a lot of what we do in infrastructure design. So here are some examples that, so this is the kind of abstraction of that particular picture. You think of a platform as the digital platform that is managing both a physical system and how agents are interacting with it. Now, the way this typically works is that the platform senses information from the physical system. And I'll give you some examples of that. This information may not be available to the individual agents that are actually in this particular system, okay? The platform then would like to use this information that it sends to provide recommendations, you think of it this way, to the agents of how to behave. Equivalent to a recommendation is probably providing them with sufficient information. There's a duality between information and the actual decision. But in order to do that in an effective way of coordination, they need to know information about the agents. So the agent themselves have private information that the platform doesn't have. So the platform is trying to elicit some private information from the agent, then provide them with a package of saying, this is the best thing you should be doing. Okay, well, that's kind of hard, because then if they adopt that recommendation, then they apply that in the actual physical system and they receive a certain reward. Okay, so that's kind of like the general picture of this coordination game that is happening by the platform. The platform, if it's a a transportation platform, for example, it could be interested in maximizing the sum of utilities. That is, it's interested in the welfare of everyone who's interacting. And you basically want to minimize congestion, and that means that you want to allow everybody to have a better experience. But if it's a platform like an e-commerce, it could actually be interested in extracting revenue from the agents. It may be interested in making money. And so those are different types of objectives that the platform can engage in, which changes the way they would actually do the recommendation. The question is, why should the agents even follow such recommendations? Why should they even care about this type of a problem? So an example here I like to think about it is food trucks. So food trucks it's called the hoteling problem, but the hoteling is the name of a person, not a hotel. Could be an example of hotels too. If you think about a bunch of food trucks and they're trying to kind of line themselves up on Mass Ave, for example, in Boston. And every day there is a sort of these people come in a regular basis. So we think of this as a game, but not a repeated game, just a game. Think of a game that it happens many, many times. So we do everything in expectation. So, okay, so what is the deal? The platform every day senses what's going on in a physical system. Okay, what is the physical system? In this particular case, the concentration of agents, buyers from the food trucks. So maybe, today we have more people because there's a conference somewhere on one street, and then maybe another conference in another street in a different day and so forth. This information changes daily, and it has a distribution, which is a normal distribution with a mean value X. Let's say that the food trucks know that it's a normal distribution, but they just never know when the mean is. So the mean is the quantity that the platform actually senses from the physical layer. So if you're a food truck, you would like to know exactly where this mean is because you want to place yourself on that mean. Okay? Let's think of it as having two food trucks, okay? They both want to know what that value is, and the platform can coordinate that activity. So what does that mean? One way, the platform can just say, look, I know what X is. I'm going to give it to you for a price, both of you. But it doesn't have to give them the exact information. Maybe it will give Z1 for one vendor and Z2 for another vendor. Okay, it can do that for a price. Okay, and if it gives Z1, let's just think of a very simple model. The valuation or the return that the food truck will get is the market share of this market. So the market share looks like this. So Z1 will get everything that is close to them, and Z2 will get everything that's close to them. So in this particular example, Z1 gets a larger market share than Z2. Okay? Okay. So why should the platform give different information? Well, it depends partially not just on the information that they got X, but also on the individual valuation that these food trucks have. So they're not uniform in the way they value this information. Potentially one food truck actually gets a lot more from each individual. Maybe one sells falafel and the other one sells Asian. And the Asian is a little bit more expensive. So for every new customer, the Asian truck makes a little bit more money. If the platform is interested in extracting revenue, then they would like to give the right information to the one who has a higher valuation, because then they make more money by getting more people, and then the platform can extract more money. However, if they did that too often and they ignored the other guy will stop listening to them. And so they don't have a free hand of just allocating the information to the most effective players. They have to balance this with the other players. And of course, a priori, they don't know this valuation. So they are trying to ask the two food trucks, so what is the gain that you get per customer in order to do this for them, to coordinate them? And there's no reason why the trucks are going to give them honest evaluation or truthful evaluation. They can lie to them and say whatever they feel like telling them because they want to maximize their information as well. So truthful exchange of information is not guaranteed unless there is a certain way this exchange is happening. So again, I would say that in every platform, there is this exchange. The platform senses something about the real world, and these guys, the agents, they have their private information. So information flows from the platform to the agents, but information flows from the agents to the platform. Okay. Think of another example. Managing a transportation system or congestion. Today, for example, the platform we think about is the GPS system. Okay, and the way the GPS it senses data on the physical system by looking at where the congestion occurs today, and it provides a common signal for everybody. All the agents are getting the same signal. We all see the same type of congestion, and then there's a recommendation of how to take a certain path that will get you to where you're going in the least amount of time, and it's not personalized in any particular way. Okay, so in a sense, even though it's informationally interesting to actually get the GPS information, it is not doing a good job in coordinating the behavior. Okay, because it's actually just telling everybody now go to the right, now everybody go to the left, and so we move from one congestion problem to another congestion problem. Okay, so how is it that this information can be allocated to coordinate the behavior of the agents? Well, think of an interesting example that happens to us in Boston. I'm sure, Cornell, you face the same issue as well. So every year around November time, we get the first snowstorm. And it's almost every year the same repeated story. We all show up to work, at 9 or 8:30 or 9 a.m. And then by 11 a.m., the mayor of the city decides to shut down the city because there's a big major storm. And everybody leaves the work at the same time, and everybody is stuck on the highways. Okay. So this is an example where this is not a very good sort of management by information exchange. It could have been done much better. And one way to do it is to prioritize based on who needs to get home first. So there are people that maybe need to go pick up their kids from school, so maybe they should be leaving first. And some people maybe have appointments with hospitals and doctors, maybe they leave, there are different priorities. So then what the platform should be doing, it knows now that there's going to be information about the closure. So it elicits from the agents information about their priorities. Again, I would say, why should I tell them my truthful priority? My kids are out of the house. I don't have to pick up anybody. I'm not going to the hospital, So I'm going to end up last in this. So I may not be incentivized to give this information. I may say, oh, I really do have a doctor appointment. So, but the platform needs to elicit the truthful information. So that's another example of, again, what is the mechanism in place that will have everyone share the correct information. The third example is one area where we're also spending quite a bit of time, and it may be a different situation. I can give that different talk, and that is in the management of electric vehicle storage. And it's an interesting example, another infrastructure example with a data market on top of it. So the infrastructure here is that, if the predictions were right and 2025, we had 40% penetration of electric cars, that never happened, but suppose that prediction was right, then every day we come to work, 40% of the cars coming to our building here, Stara, there'll be 40% of the cars that wanting to charge. And 40% of the cars trying to charge in Cambridge, most of the days will break the distribution network. There's just not enough capacity in the distribution network. And that would mean that over a broad area in Cambridge, we have to upgrade all the distribution networks. So that's a solution, of course, kind of in preparation for this particular kind of change in going electrification change. But short of doing that, can this problem be managed a little differently? And the answer to that, well, lies in the fact that these EVs are storage components. They themselves have storage elements. They're trying to charge, but they also store electricity. So could they have been managed in such a way that we never exceed the peak value on the distribution network? Okay, well, there is, of course, because but what's needed is an exchange of information. What is the information I need? I need from each EV to truthfully tell me the time they plan to disconnect from the grid, from the charging station, and how much charge they need before they leave. Let's assume that I can do bidirectional charging, then I can manage this farm of batteries. Because sometimes what I do is I'll discharge to charge others. I may charge the ones that have to leave early fast, and then I leave the others. And by this management, I can do a lot more than just charge everybody at the highest rate as soon as they come into the parking lot. So it's a management problem. It can work really well, and there's a sort of an optimization problem to do it if I know all the information necessary. So how do I incentivize the players to, basically, so the physical system is really the capacity of the distribution network, and the individual agents, now the cars, need to communicate information about their deadlines or when they plan to disconnect. In some of these systems, obviously, what's going to happen is that you are going to benefit from participating in this game, but in this particular structure, in that you are rewarded for the information you provide. Okay, and so part of this, the reason you would participate is that you will do better that way. And rewarding could be that you're charging at a cheaper rate. Rewarding could be that we're giving you an incentive by cutting some costs. And you are rewarded for sure if the distribution network doesn't break. Because if the distribution network breaks, nobody gets charged. And so again, there's a lot of different ways to think about it. So we talk about a payment function going back and forth between the platform and the agents, right? And that's an important part of any mechanism that we describe. So those are some examples that justify this information monetization coordination problem that I'm describing. So let me sort of get into, and maybe I'll just get through half of my talk. Let me say sort of a little bit about, why this sort of problem is different than, it's truly about information exchange and information sale. The platform has information to sell the agents, and agents have information to sell the platform. Why information or data sale more complicated than, say, physical products? So, of course, in the broader sense, there is the replicability of information. Information can be replicated at a zero marginal cost, which means that when the, say, platform senses something about the physical system, it can sell that information or give that information to many, many different people. So why is that critical? Because if it was one product, then one person gets it. Nobody else gets it. But now, if it's one product, it's an information product, many different agents can get it. That means that there's an externality effect, because I would rather know a lot of information, but as soon as my neighbors also know this information, maybe the value of the information drops, because we're all now sharing this valuable information. So externality become an important piece. So this is the last part here. Competition and is created by the externality of selling information. There's another piece to this, which is versioning, that is different than a product. If you come in and auction, say, a house, you're going to get the house. But if you come in on an auction for data or for information, I can give you the information. Or if you pay less, I can give you a noisy version of the information, And so I can version it in different ways to sell it to you. I don't have to give it to you in its pure form. That enlarges the space of products I'm able to sell you based on that particular information. And the other player in all of this is the heterogeneity of the utility functions of the buyers. So in general, I'm focusing the talk here on context where the buyers share similar kind of value function, in the sense that if you're trying to charge your car, you're trying to charge in the cheapest possible way. If you're on the highway, you're trying to get home early. But in a larger perspective of a data market, which is kind of, this applies it broadly, it's not clear what my utility is. My utility could be very different from the utility of another person. And that heterogeneity changes the way the value of the data is computed. Every person has a different value. So that kind of complicates it. You can think about it, say, if you're buying a house, the utility is to live in the house. I mean, the utility is very similar. Now, there may be details to it where I don't care about having 3 bedrooms versus 2 bedrooms, or so kind of variations, but the value it brings in is the same. Here, the data comes in completely differently in terms of the impact on people. Okay. So then looking at the platform job is 2 things. Either I think of it as a digital platform's job to coordinate behavior because of some social welfare, in which we think of it as it's allocating information to maximize welfare. Welfare meaning just the sum of the utility of all the agents. Everybody is getting something good, okay? Versus as I said before, the platform is a player in this game and is trying to maximize their revenue, okay? And there are some nuances and differences that come from these particular problems. But when and I would say in digital platforms, like, for example, the reason I keep picking on digital e-commerce platforms is that you can imagine that Amazon actually is trying to provide a utility for all the agents, all the sellers to sell on the platform. But we have class action lawsuits right now sitting in there that accuses Amazon of price fixing. And one of the obvious thing that happens with Amazon here is that they have their own shops. I mean, Whole Foods is an Amazon. Whole Foods sells on that platform. And so, in a sense, Amazon, knowing more information, is able to actually extract more revenue by saying to other people, look, I mean, if you don't do this, I'm going to let my prices on Whole Foods to be cheaper. And so I can actually kind of change the behavior on this particular platform. So the idea of engaging in antitrust behavior is actually it's quite possible. And maybe in a way, I'm here trying to show Amazon how to do this, how to engage in antitrust. But of course, in general, the way we think about this is that if we know the mechanisms, then we talk about how to prevent bad behavior. If we don't know the mechanism, we cannot prevent bad behavior. Okay, think of it this way. Information allocation in this information management, okay, is equivalent to recommendation. This comes from pure game theory, right? Agents are going to be playing rational games. They're going to be maximizing their utility. And so if you're providing with information, it's as if you made a recommendation of what they should be doing. So this is an equivalent called the revelation principle. A very important component to everything we do here is what we call the obedience constraint. That is, just by allocating information to people, why, as I told you about the food trucks, why should the food trucks listen to this coordinator? There's got to be something in there that is benefiting everybody. If it doesn't benefit me on average, I'm not going to listen to you. I call that an obedience constraint. That is, information design has to be constrained by me following this recommendation that you give every single time. However, the limitation here is that the platform doesn't know the utilities precisely because of private information, okay? And so that's a limitation, so that pushes us to a mechanism design. So I don't know how many people are familiar with the idea of a mechanism design, but you should be thinking of a second price auction as an example of a mechanism design. So let me explain that, and then I'll tell you how that generalizes. So in an auction mechanism, if you have let's say a private auction, you have a house that you're trying to sell, and let's say this house is in Cambridge and it's worth it's worth somewhere around $1 million. Okay, Okay, so now there are multiple people that are they're coming to bid on this particular house. So how would you bid? You know, roughly it's $1 million. Maybe it's somewhere between 900 to $1.1 million. You know, it's a $200,000 error. How would you bid on this house? Well, if you engage in an auction, it's always an auction. You put the silent bid, and then the owner will pick somebody, right? Most of the time, they pick the highest bid. Okay, so I really like this house, and I would want to win it, and so I want to bid higher than the asking price. Maybe the asking price was $1 million. I want to bid higher than the asking. This is the problem we have in Cambridge all the time. People don't know how to bid because they want the house. The house really, the value to them is just $1 million. But because they want it so badly, they bid higher than $1 million, and they don't know by how much. It's kind of like an unstable methodology for bidding. If I put more than $1 million, and then I discover that the other people put 950, I feel like I put money on the table, you know? And if I underbid, I'm always afraid that somebody's going to overbid. It's very confusing to me. I can't even bid my own valuation of the house. If I think it's $1 million, I cannot just justify bidding $1 million. So second price auction simply says a very simple exercise. Why don't you bid? Everybody bids, the highest bidder wins, but pays the second bid. So you don't pay your bid, you pay the bid that is right below you. You can prove that this is a stable mechanism that in fact results in everybody bidding their valuation. Now I'm comfortable. I'll bid what I think the house is valuable to me. And I will not be worried about putting money on the table, because if this house is not valuable to anyone else, I won't pay that amount, I pay less amount. And if this house is more valuable to other people, well, I would not win it, but that was okay because somebody else wanted it more. And they paid more for the valuation. These are called mechanisms. And what they do, this mechanism does, it elicits the private information without asking for it. Nobody comes and tells me, tell me exactly how this house is valuable to you. I bid that precise value. Okay. So in order for back to our example, in order for the platform to elicit these private information over here, what needs to happen, it needs to set up a mechanism. What is a mechanism? Is really a recommendation parameterized by the private information. Okay. And then what happens is kind of like a menu of recommendations parameterized by this private information. And then what happens, the agent should come and pick the one that corresponds to theirs. And if it's designed correctly, they should pick the one that is done to them. Okay. So this is the way we think about a mechanism, is that a menu of information allocation. And as I said before, that is equivalent to a recommendation. So a menu of recommendations, okay? And then, of course, to that, there's also a payment function. So I give you a recommendation and I give you a payment. And what you need to do is to decide, they're all parameterized by your own private information. You pick the one that you want. And when you want it, what we want the design to do is to elicit you picking the truthful value, the one that reflects truly your private information. And then you will be something called incentive compatible. That is the utility that you get from picking that solution, that particular recommendation, including the payment that you will put on it, is actually the best you can do. You cannot do any better by following any other recommendation. It's called incentive compatible. Okay, I break that into most importantly, just being obedient, and I'm going to explain that a little bit. They're not equivalent. Is that I just want you to follow the recommendation, be truthful, and follow the recommendation. Okay. There's something called individual rationality. I'm not going to get into that in this lecture. We don't have that much time. But individual rationality simply says that you ought to also participate in this thing, completely participate, and not take yourself out of this particular mechanism. So this is what we call information plus mechanism design. There's an information design by the platform, but they set it up in the form of a mechanism design to elicit the private information. Once they have the private information, they make recommendations based on the state that they know about the physical system. So there are 3 different models that I have and 10 minutes. Okay. And so the first one I want to tell you about is the easiest one, and that is a linear model without any game. Okay, there are no games. Okay, so basically the way it works is as follows. There are four different firms selling different types of shoes. Okay, and they are looking for information about the consumers. Okay, so that is equivalent to the ad market situation. So the information they get to the consumer is by allowing them to advertise to a specific consumer that is maybe logging onto their Amazon or New York Times or whatever platform that they're using. Okay, so the way it works is as follows. The ad market, basically everybody competes, so I log in onto New York Times, and there's a piece of real estate there, and every firm is competing to advertise something for me. Okay, so one way is that there'll be one space and one firm wins. One of these firms wins. But then now people are doing, eBay does that, a lot of platform does that. They show multiple things, but they show them in some order. So maybe this guy gets the top one, then it gets number 2, number 3, and number 4. Maybe only 2 spots, 1 and 2. Okay, so then the utility that the firm gets from looking at me, basically marketing to me, of course, is proportional to them being taken the first location, but they are losing because this guy got the second location. That's the externality effect. So I gained by being number 1, but I really don't like the fact that this number 2 is my competitor. Okay, so there is a utility, but there is a disutility. Okay, so this is modeled like a simple linear model. There is no game that the firms are playing. It's just a very simple linear relationship where if the platform allocated X, which is your number 1, your number 2, your number 3, that's the information allocation, I get my utility VIXI, but I lose all the relative utility of XJ that affect me. So it's kind of like a graph. Everybody that's connected to me is subtracted from my utility. All right. Now, the interesting thing about this is that, okay, so now you think of the platform. A platform would do wonders if it knew all these valuations, if it knew the VIs and the AIJs, but it doesn't know them. Because it doesn't know them, it has to set up a mechanism that elicit these things. Okay, these mechanisms look like second price auctions. They're a little bit more complicated than that, but they follow something called the Meyerson's approach, extended from R1 to Rn. It's a sort of an interesting story. But I don't want to focus too much on this example because that's too simple. As I said, utilities can optimize if they knew the utilities, but they don't know the utilities, so they try to extract it from people. Very quickly, I want to tell you the solution to this problem because I want to jump to the more interesting case when the agents are actually playing a game at the downstream. So the solution here is what's called a posted price auction, okay, or a fixed rate. So basically what it is that in a simplified situation, the allocation you get is either you're on or you're off, okay, 0 or 1. And you get an allocation of data if the positive valuation you get exceeds all the negativity that comes from the other people. Not that what affects you, what you affect other people. So VI here is my utility, and these are all the negative things I exert on other people. If this is better, then I get allocated. In the revenue maximization problem, there's an interesting result by Meyerson's that show how revenue maximization is equivalent to welfare maximization by doing something called virtual valuations. You map the valuation to a virtual valuation. It's a technicality, I don't want to get into it. The result looks the same, but instead now of having the actual valuations, you're mapping them through something called virtual valuation. You can analyze the solution. There's a lot of interesting stuff here that I want to tell you. The only thing I want to say is that maximizing revenue is not an efficient solution. That is, if if the platform is maximizing its own revenue, it actually doesn't maximize welfare. It doesn't do well in terms of welfare. It actually tends to be doing less in terms of allocating good information. So here is a welfare maximization characterized by the red lines. And what does it say? There's a function of the valuation, symmetric case, one V1 and V1 to 1 to 2, and everything is equal. So two players. And what you see here is that the welfare maximization is giving the full information to both players for larger values of valuations, while in the case of revenue, it's not. It's restricting the information by a lot more and yet extracting a lot of energy, money. So competition seems to allow, increased competition allows the platform to extract even more money. So that was an old model that we worked on, a linear model. And maybe in the next 5 minutes, I'm just gonna show you just one simple mechanism for a game, similar to the food truck game, but simplified. Okay. So what is that game? It's a two-player game. Okay, so now what do we have? We have a situation again where the digital platform is regulating two agents. The two agents are trying to match the state that the platform knows. The state of the platform is the physical state. Okay, so and that's given by a parameter theta. So let's say in the food truck case, theta indicates the mean of where people are concentrated today. So let's just think of this as a very simple example. They're either on the left or they are on the right. Okay, that information is only available to the underlying to the platform. Okay, if the agent knew that information, they will match it. So this is a matching game. So you look at this 2x2 game, it's a matching game. Everybody would like to be on theta if they knew what theta is. Okay, and they will get a reward 1 minus alpha, 1 minus alpha, where alpha is an indication of the competition. If in fact A1 get it right, but A2 doesn't get it right, A1 gets a full reward 1 and the other guy gets minus alpha. Same thing here symmetrically. And if they both get it wrong, they both get 0. So it's entirely a matching game, and it has dominance strategy. So the first player will always play the correct state, and the second player will always play the correct state. So an easy game. Okay. Now, the way the game is played is that there is the state that is revealed to the platform, that's theta, and the players don't know it. Then there's the valuation that is revealed to the food trucks. So the way you think about it is that every day different types of food trucks come in, not the same guys. So they have different valuations realized on that particular day, V1 and V2. Okay. So the utility of the food truck is VI times whatever they get. So if they match, so their utility is written as one for every time they get the answer right, and they lose alpha if the other gets it right. Okay, so then their utility is the VI, which is private, times this particular pi, which is known to everybody. Okay, so again, imagine the game. So what the platform is trying to do, if the platform knew the valuation VIs, it can do a lot of different things. Okay, but if it doesn't know it, it has to elicit it through a mechanism. Just imagine there are so many different types of situations you can imagine. I want you to imagine the simplest possible one, which is that suppose these two players, the two guys here, don't know theta, and there's no information about theta. What would they do? Well, they may know the prior information about, we'll assume here that the statistics are known, so the prior information about theta is known. So if I know that, for example, it's most likely that theta is on the left, okay, I will always play left. And so because it's symmetric, the other guy will always play left. And so everybody plays left. We both get 1 minus alpha reward times our valuation multiplied by the probability of us being correct. Okay, I can do way much more than that by coordination. This is not very good for both players. And so you can improve a lot more by engaging in this game of learning theta if you provide your information. Okay, well, as I said, then what is the problem from the platform perspective is to design the recommendation. Is to say, look, I'm going to give you a function, maybe a distribution, a random function distribution, that is a function of your private information and your, of the underlying state and the private valuations. Okay, that's what I'm going to design. And I'm going to try to design it to maximize some objective function. I only have one constraint right now that I care about, and that is I want you to be obedient. Okay, so the obedience constraint says that when I apply this A to both of you, then individually you do better than deviating. Individually you do better. Assuming the other player takes my recommendation, you do not have an incentive to deviate. So I force a Nash equilibria on that particular solution. That's the obedience constraint. You can write it out. This is a simple game, and it turns out to have a very simple characterization. For this particular game, the recommendation is obedient if I tell you the truth more often than the prior information. Pmax is the maximum, the probability of the maximum, what is it? Okay, so um, theta equals 0 has one probability, theta equals 1 probability, Pmax is the largest of the two probabilities. I need to give you the truth higher than the maximum probability of the two. If I do that, then I'm giving you more information because you can always play the Pmax. I'm going to give you something better than Pmax. That turns out to be the simple obedience condition. Because of that, I can solve all of these problems analytically. So here is the simplest thing that I want you to sorry. Okay. So let's say that I'm interested in welfare maximization. Okay, that's the platform. You can write down the sum of the two utilities and massage it a little bit. And you get that the welfare is equal to V1 minus alpha V2. Those are valuations. Valuation of the first guy minus alpha of the second guy. One if A1 is getting theta, and then the opposite of that, one for A2 getting theta. If I didn't have an obedience constraint, then the maximum welfare actually is given by these curves, the curves that characterize when this guy is positive and when this guy is positive. I will only assign positive values if this expression is positive. Okay, so I'll give a 0 otherwise. So the solution will be concentrated in this area. However, that means that I'm actually giving wrong information to both guys everywhere else. So the concentration is on the right, and I'm telling everybody go to the left. Okay, but for obedience, that is for people to come back and follow my recommendation, I am restricted to how much distortion I can have. And the restriction says that, okay, below this curve V star that is obtained from the obedience constraint and symmetrically, you always have to give me correct information. So the diagram then says that the distribution of the recommendation, anywhere if my valuation lies below V star, then I get the correct information. And if my valuation below V star, but the other valuation is higher, I get obfuscation. So one guy is told, go to the left when the group is coming to the right. Notice this is sort of interesting, right? I'm telling one of these truck vendors, the concentration is over there when actually it's in the other side, okay? And what I'm doing in this case is I'm allowing this one guy that goes to the right to get the maximum benefit. Next day, when the valuations switch, the other guy gets it because they're sampled from some distribution. In the long run, everybody is benefiting better than both of them going after the same people. And that's the coordination game. I'm getting higher welfare. Is this an implementable in the sense of incentive compatible? That is, this is assuming that I knew the valuations. So could I elicit the valuation through a mechanism? And the answer is yes. I can't explain to you exactly how, but basically the way you want to think about it, with obedience constraint, I can achieve a certain welfare higher than the previous welfare. So I'm giving you better performance. That delta of revenue, okay, that delta of revenue is an incentivize everybody to participate, and it is revenue that can elicit that will make this implementable. That is, I can actually, because of this delta, I can pay you sufficient amount of money to actually have you contribute exactly your valuation. And that's the mechanism design part of this. Turns out that and I know I'm running out of time, that the problem of revenue is a little bit more complicated. And what's interesting is that there will be, so this is the way the recommendation is depicted on the set of valuations. And this dark area over here is an area where if the valuations lie in, neither party gets the correct information. It's a pure obfuscation. Everybody is sent to the wrong side. And somehow this is sort of interesting about revenue maximization is that the creating a need for this for this platform that sometimes you want to emphasize that that you could do very badly without this platform, and so you can do it even for both guys and then still extract more revenue. But the point is that maximum revenue really doesn't care about maximum efficiency or welfare, and so this is what happens over here. I'm just going to try to say one last thing here, a couple of last things. One is the higher the competition, the higher the amount of revenue extracted in the maximum revenue. That is, the more alpha increases, the more money the platform can extract from people. Okay? And the less welfare is. So the welfare somehow drops and the revenue extracted by the platform is more. And so competition creates a situation for the platform. One is to do a lot better in terms of welfare coordination, but if it actually wanted to extract money, it can extract a lot of money from the players. And of course, this is a very generic theory. The question is for us in management of infrastructure, we'd rather everybody is solving a welfare problem, not a revenue maximization. But as I said before, we cannot just say that that's the only thing we do. The third part of the talk that I would not get into gets into situations that are more complex than what I described in this binary game. The binary game has a dominant strategy, so everybody knows how to play. But what if the game doesn't have a dominant strategy? How does that change the interaction? Much richer type of problems. So we have formulated this problem as a Gaussian game now played between these different people with an intermediary in the middle. And clearly, I'm already after 1 o'clock, so I'm gonna stop here, and I don't know if there's even any time for questions.
Yeah, thank you, Dr. Dahleh. If your schedule permits, you could just go over it and like since this is gonna be recorded and stored on YouTube, they could always come back and view it at a later point. So
Okay.
yeah,
So I can do another 10 minutes. So let me describe
yeah,
that.
yeah,
Okay.
yeah.
So then let me just say that here's a situation now where, again, we want to look at more general problems that arise in economics and so forth, and clearly in infrastructure. Now I have many, say, buyers or players. Each has slight change of notation. Each has its own private information as theta. And the intermediary has a knowledge of the state or the environment, which is W. It's kind of slightly different notation. And the utility now is a generic utility of a sort, so it's a little bit more complex. So the utility of each agent has a quadratic utility AI squared. They have a cross utility. So A is their action. So they get something for their particular action. They get something that is related to the correlation of their action with others, AIAJ. And then they depend on the state of the world and on their private information in this linear way. Okay? I'm going to show you a couple of examples where this makes sense, okay? And so, of course, each player has a best response, which is to the other players, which is obtained by differentiating this and setting it equal to 0. So you get that the best response behavior of each one of the player is a linear function of the other players, okay? So that's nice structure for the quadratic game. Okay. The two examples I will focus on the Corno and the Bertrand. Okay, the Corno game is known as a strategic substitute game. The way it works is that you have multiple firms producing similar products, and they're trying to decide how much of that product they want to produce. Okay, so they are deciding the quantity of the product that they want to produce. The private information is their marginal cost of how much it costs them to produce that product. Okay. And the underlying state is the demand shifter, and that is something that they don't have access to. The usual thing in a corner game is that the price associated with that product is given by some linear function, and the linear function is shifted by W, which is knowledge of the platform. It's affected by the quantities produced by the other competitors and the quantities you produce. In this particular case, R is a negative quantity because the more people produce, okay, the lower the price is going to be, okay, because that's it's a strategic substitute. So if a lot of people are producing a lot of the same thing I'm doing, then they actually kill my ability to sell. So if you plug in the utility as the number of quantities times the price minus cost, you go back to the utility function that I had with a particular structure. The Bertrand game is a game on price. So what you are trying to decide is the price you want to give to a particular item. Theta I is still the marginal cost that you have, and W is the demand shifter, same kind of a thing. Now the demand for the product is a linear function. So kind of a different dual sort of representation of Corno. So the demand is the shifter. It depends on the prices of everybody else and the price that you have. Here, R is positive. Okay, that means that what is happening is that the demand is higher if everybody is increasing their prices. Okay, but you will reduce the price. I mean, that you'll be incentivized to reduce the price to sell more. So this is kind of the way this thing actually works. So in this case for us, we think about it as a strategic complement, and R is positive. Okay, and the beauty context is another one that I don't have to get into. So let me just describe very quickly the general results here. So now we have a similar game. What is happening is that the platform senses the underlying state, which is W. It wants to do information. It wants to coordinate the activity of everyone. So it wants to make a recommendation on what decision each one of these players made, but it doesn't know the private information. So it needs to elicit the private information. Okay? It's kind of the same story. We will assume that the prior on the state is normal distribution, and the prior on the individual private information is also a normal distribution. This is common knowledge. Okay, common prior. Okay, and then so what is going to happen is that the mechanism is going to be set, everyone is going to agree to play, and then there will be exchange of information, and then a realization of a strategy. So the mechanism design is a way is built on top of an information design with elicitation, sort of based on Bergman and Morris's work, and then there is a lot of other related work. So because the assumptions are normal distributions, you can show without loss of generality that the recommendation function is also Gaussian conditioned on the parameters theta and W. That is you're trying to create a recommendation which is a normal distribution. So that means that the joint probability distribution is normal. A, theta, and W. A is the recommendation, theta is the underlying private information, W is the state. So we are designing the joint probability distribution. That's what we're designing. That's the first part of the mechanism. And we're going to design also the payment function that goes with the mechanism. All right? But the point here is, of course, how do I design this joint function? It has to coincide with the marginals. So if I take out A, the distribution over theta should be the prior, distribution over omega should be the prior. And then, of course, it has a mean and a covariance, and the covariance have to be a positive definite matrix. Okay. So I don't want to get too much into the details. I do want to say that the same thing occurs as the previous example, but the intuition is slightly different. And that is, if the mechanism Sorry. So let's say that the first thing is if the information designer, the platform, knows the particular private information, then we are in the realm of information design. Okay, just an information because they know the parameters. And what they have to do is to allocate the information, equivalently allocate the recommendation subject to an obedient constraint. Same thing as I did before. The obedience constraint exactly says that the AI is the maximizing solution of the utility. Okay, so I can get a linear characterization of what AI has to be to say that it's an obedient constraint, subject to also the positivity constraint. Positivity constraints are important. So if I actually sort this out, and I'm going to skip this, turns out that we have a nice parameterization of all obedient constraints in terms of an ellipse. Okay? Kind of all the obedience constraint has to be either on the ellipse or inside the ellipse. Without getting too much into what is the center, the two powerful parameters in the characterization of the strategy is how is the strategy correlating. So recommendation for the ith agent of what to do, how does that depend on other people's private information? And how does it depend on the underlying state of the world? Okay, those are the two things more or less that characterize everything else that I need. Okay, modulo one factor, which is an additional randomization that I'll tell you about it in a second. So this corner over here says that this is basically completely Bayesian. There would be no real correlation of theta j or omega. Everything is done in expectation. Nobody is revealing anything. And this corner over here is the complete information Nash equilibrium. If everybody knew theta and everybody knew W. This corner is everybody, there's no correlation on theta, so Bayesian with respect to theta, but then you correlate on W, and then vice versa. Here, this correlation on theta, but no information. So we get that corner points. This area over here is an interesting area that I mentioned, but will not spend a lot of time. This game is actually more complicated than the discrete game in the following sense. It turns out in the discrete case, two things that were important. One is the incentive compatibility, which says that this is the right thing for me to do, does break into obedience and truthfulness as separate conditions. That's first, I'm obedient if the parameters were known, and then assuming the strategy, I will contribute my true information, kind of divided into two. In the case of this particular game, the two-step game doesn't always give me true incentive compatibility. That is, if I do it in two stages, there is an incentive to deviate. This region over here characterizes all the obedience strategy that are not necessarily going to result in a separation between obedience and incentive compatible. We have to worry about those because there's an incentive to deviate in this area if we solve the problem in steps. Okay. Interestingly, what happens into the maximum welfare, and I'm going to tell you exactly what's going to happen here. So the interesting thing is that this gives me the characterization of all obedience strategy. Now you want to maximize welfare subject to obedience. So you write down the Lagrangian. The derivative of the Lagrangian in terms of the Lagrange multiplier looks like this green curve over here. Okay? And you have these different situations. Either the green curve starts, so you're looking at as a function of lambda, the Lagrange multiplier. If R, remember the competitive factor, is negative versus R is positive. If R is positive, the solution starts outside the space. As lambda increases, it hits the parameter, it hits the boundary. As soon as it hits the boundary, that's optimal. If R is negative, it can start inside or outside, but it could start inside, which means that wherever it starts, that's the optimal solution. That's closest to the boundary. Okay, nice. So the first observation is that the optimality is occurring in the quadrant, the positive quadrant. The gap over here is the amount of improvement in welfare from the complete information case. That is, complete information is not coordinated. If everyone knows all the information, they're going to jump into the same place at the same time. They're going to go to the same shop, after people at the same time. With coordination, I'm actually getting more welfare. welfare can be much more if they are competitive. The kind of the strategic strategic substitutes with the corner game, there's going to be a lot of competition, and coordination can actually give a lot of value. Interesting about the properties of these solutions. One interesting property is that in the case where R is negative, so they are competitive, then the way the platform is coordinating is anti-correlating the actions. So AI is anti-correlated with AJ because that's the better way to do it. You want today you will get this, and tomorrow you get something else, right? And so I don't want you all to do the same thing at the same time. In the strategic complements, you actually align them because they are actually adding to each other. I sell cell phones, and you sell the case of the cell phones. The more cell phones I sell, you sell more cases. So it's actually aligned. So the platform is doing the right thing in the coordination, telling them to do things together. So it's actually aligned that way. And there is, of course, implementability is, can I now find a pricing function that will actually make this incentive compatible? And the answer is yes, but I won't get into that for the second. I just want to say that the optimal revenue situation also has similar properties of the optimal welfare in the anti-correlating and correlating. It works the same way. If you look at a property of the optimal revenue solution, it puts a lot of weight on the state, less weight on the private information. Kind of interesting. Again, there's a lot of insights that one gets from writing these solutions, but these are some of the interesting insights. Why? Because the way you extract revenue from the agents, you're extracting revenue because you're giving them information about the state, W. But they are minimizing how much you take from them because they're giving you back information about theta. Okay, so that's what we call the information rent. Information rent is a value to the individual agent. By correlating less and less on their values, the platform is giving them less and less information rent and extracting more and more revenue. And so you see this characteristic of the solution putting more weight on correlating the actions directly on the state rather than the private information. That brings us to a problem that the platform will face because of doing this, and that is the randomization. So it turns out it's really interesting that if R is positive, and these are strategic complements, the solution is the deterministic function of theta and W. So I said it's Gaussian, jointly Gaussian, but it's actually a function of theta and W. Okay, linear function of theta and W. In the case when R is negative, that is when there's competition, not complementarity, but substitutes, and it wants to anti-correlate, sometimes the solution has additional randomization. That is, adds random components to the strategy. And the kind of intuitive reason behind this is that in order to anti-correlate the actions, but at the same time, putting less weights on the private information, you need to throw in randomization to anti-correlate. Okay, and you see here the ratio of how much uncertainty you have in the private information divided by the uncertainty in the state of the in the underlying state. If this ratio is high, then we have less randomization. So this is the region. This is the region where this line cuts off for, say, for revenue is the dotted line. The cuts here in between these two values, all the solutions are randomized. Outside they're not randomized. As you increase the value, you reduce the randomization. As you decrease the value, you increase the randomization. And the way intuitively you think about it, if you have a lot of uncertainty in the underlying private information, you have an ability to anti-correlate with less randomization. If there's no uncertainty, too much uncertainty in the private information, and you have to throw on in your own randomization. So you kind of start understanding the architecture of the control strategy by analyzing the solution that comes out of this problem. I think this is a good place to stop. There's a lot of insights that we learned from these type of solutions, but I wanted to say that, I gave you in a way a linear formulation that doesn't have a game downstream, and then I give you a game in the downstream, which is more of a realistic situation. Every situation we think of in infrastructure, agents are engaged in a game in the downstream situation. And this is a combined information and mechanism design problem all the time. And the point is that this intermediary can do a great job in coordinating the behavior. And the coordination increases the welfare. We can cut down congestion. We can stay away from breaking the power grid, in the distribution grid, and so forth. But it requires this cooperation in this particular mechanism design. If the platform is focusing on maximum revenue, then the solution is not efficient and it's not doing maximization of the welfare. It's kind of like contradiction to the welfare of the agents that are engaged in that particular game. It's not crazy to think that whether it's welfare or revenue maximization, that not everybody is always getting all the information right. That is, you are told to do something that is not necessarily the optimal thing you would think you would do today. And that obfuscation is a coordination mechanism. It is the way to actually get better coordination between the players, is by saying, today you actually going to go to the left, there's a congestion there, and then we're going to let a lot of people, other people, go to the right where there's less congestion. If we sent everybody to the right, there would have been a congestion and nobody would have benefited. So it's kind of a coordination requires this obfuscation or distortion of information. And also I wanted to say that the seller can extract a lot of information with more competition. And there's a lot more in the paper on archive on the second game that I mentioned on the architecture of the solution and some of the insights that we learn from solving this particular problem. So with that, I just stop.
Thank you so much, Dr. Dahleh. There are a couple of questions, but maybe I can direct them to your email in the interest of time, or
Okay.
how do you prefer
I have
to?
until 1:30. I can
Okay. Maybe I can just ask one question from the chat, and yeah. And could you share your insights on whether explainable reinforcement learning could potentially be used to identify incentive compatible and individual rational mechanisms?
I mean, I think you can set up any data in this way, and an algorithm is a data set, right? And the utility is coming from how much, this explainable in this case, how much a particular stakeholder is understanding the value. A lot of these problems, have there's a generality to this. The question is, can you adapt can you work out the theory to get the insight? That's really the issue here. There's a lot of work to be done to be able to solve a broad set of questions. But to think about an algorithm as a data point is a common thing, and algorithms are data. And by acquiring an algorithm, you actually get a certain utility. And so the story there is very similar. It's just a question of whether you can work through the details of how to characterize the value, and what is explainability, and what is the value of explainability, and how does that play out in a sort of in a multi-agent type situation.
Thank you. And the next question is, could you share your thoughts on effective mechanism design to build trust between agents and the platform? How can we mitigate dishonest reports from agents?
The mechanisms are designed to mitigate dishonest reporting, and so the idea is that, and it's a very clever approach that came up, many years back, of saying that, well, there is a reward structure, and the reward structure you will not utilize if you don't share your correct information. The same thing as I said with the auction design. It's a clever idea of you put the mechanism in place where the best solution for you is to share your correct information. If you don't share it, you don't get the best outcome of the game. Already the game is stacked that way. It requires a little bit of thinking to understand, how come, no one is asking me and no one is verifying. No one is verifying. This is a mechanism that naturally does the right thing. So it's our, in fact, yeah, I mean, I should have said that at the beginning, kind of trustworthy isn't something that you can just simply convince people to do. Trustworthy has to be a design requirement, and mechanism design is a way to think about trustworthiness.
Thank you. And perhaps last question. Can we relax the quadratic utility and Gaussian distribution on the prior assumption? How would you approach that?
You can relax. I don't know how far the theory will go. So the first example I gave you was a discrete case. It didn't have any quadratic structure or anything. It was discrete, and so everything is you know, linear utility, but discrete game. Um, so the second part, all the nice result. I mean, the paper is an archive and we're updating it, but the sort of all the detailed analysis that we can give, characterization of all the strategies, and I mean, it depends on the quadratic cost and the Gaussian assumptions. And if you take that away, then of course you can formulate the problem, but I don't know how far you can push the solution. So yeah, the formulation can be extended. I'm not sure how much of the solution, but it would be a nice, of course, piece of work if it's done.
Thank you. And personally, like I come across this line of work on Bayesian persuasion.
Yeah,
Yeah, so I
yeah.
was just wondering, like, if that is some or like extensions of those work could maybe, yeah.
Bayesian persuasion is a big part of information design problems, and it's very another kind of angle of looking at the same type of problem for sure.
Thank you. And yeah, I think that's all the questions we have for today. Yeah. Thank you so much for your time, Dr. Dali.
My pleasure.
Yes,
I hope
yes.
you enjoyed it. Thank you.
Yeah.
Bye.
Bye bye. All right, everyone. See you next week. And just for your information, next week the seminar is gonna start at 2, but I'll send an email just to remind everyone.